Hi there, this is the RPS Project. I'm Richard and today I'm going to have a look at low pass filter. This is an RC passive low pass filter. That means I've got a resistor and a capacitor. RC, there we go. It's passive because there's no active components in this, just two discrete components. Filtering out frequencies. Now low pass, because as far as I'm concerned, the way I read it is that it's going to allow the lower frequencies through, and then the higher frequencies are going to be, as it were, filtered out here with this capacitor to ground. So that capacitor is quite important. So I'm going to use a 1K resistor. I'm going to leave that the same, but then I'm going to change this this capacitor to different values and see how that affects the frequency of what's basically allowed to pass through to the output and what gets attenuated depending on that capacitor. Very simple equation for this. Frequency equals 1 over 2 pi RC. Very simple equation to use, and I'm just going to use that to work out what frequency I'm going to get dependent upon which capacitor I'm going to put in here. And I'm going to change the capacitor and see what happens. See how much change it gives me dependent upon that capacitor. Now I've also drawn a chart here. It says frequency against the amplitude. Now it doesn't just cut it off straight. So you put your capacitor in, you work out what frequency it's going to cut off. It doesn't just come along and then stop. It actually attenuates it over a period of time, as the frequency increases. So that's the amplitude, and whatever that amplitude is, that's the frequency coming in. And as I increase the frequency, it gets to the point where it reaches the supposed cutoff frequency where it's going to start to really attenuate it. But actually you've got this small area here that attenuates before you reach this point here, which is the cutoff. And from what I've read, that is supposedly about -3 dB. There are calculations and an equation you can use to work this out properly, but I'm not looking at that this time. What I'm just looking at is this capacitor and frequency against how much it'll attenuate. So basically, will I get like 100 Hertz before it attenuates, or will it be like 10 kilohertz before it attenuates? And that's all dependent upon this capacitor. That's what I'm going to be looking at in this video. So that's what I want to see. Changing that capacitor, what effect does it have? So anyway, enough about me jabbering on. Let's get and have a look at it. Okay, so here we have on the breadboard my little setup. It's all very simple. Just a resistor capacitor. That's all we need for this. Signal comes in through the resistor, and that's my output for my signal, and then goes through the capacitor to ground. So very simple. Going to leave the 1K in all the time, so it's always going to be a 1K, but I will be changing that capacitor to see what I get. I've done some calculations as to what I'm expecting, so we'll find out if I'm right. So I'm just going to pan up now. Oops. Get that on the scope. Right, so starting with the 1K 100 nanofarad, I've got at the moment half a volt, and it's on 500 Hertz. So if I turn that on, and you can see that at the moment it's slightly clipped, but then in this type of circuit there's always going to be a slight bit of loss unless you're way off from the cutoff point. So what I'm going to do is just stretch that out a bit. I'm going to turn this frequency up until we start to see it come down, and we need it to be really at, according to this, 1.59 kilohertz or 1.6. So that's at 1.6 kilohertz. And as you can see, it is being attenuated. We've also got a phase shift in there as well due to that capacitance. Now the thing with this is, I looked at this and gone, well, hang on a minute, we've got a phase shift. I mean, not a phase shift, we've got a attenuation before then. Now this is something I've not done the calculations for, but when we reach the point where the frequency is being attenuated, it isn't just like a sudden drop off. It's a slightly gentle curve, and then it comes down at a particular rate. And on this occasion, with all these passive filters, when we reach, supposedly when I reach the point at which it starts to attenuate, I'm already at 3 dB, minus 3 dB on the frequency of which we started at, which is 1.6 kilohertz. There is a calculation. It's a very simple one for looking at that, but I'm not looking at the moment. I'm just looking at the fact that as I have different capacitors in there, I'm going to have a different frequency at which it's going to be attenuating. But obviously if I turn that up, I'm now at 3 kilohertz. We're really starting to lose that signal. We crank that all the way up to say 5 kilohertz. It's really heavily attenuated that signal, so basically I'm only getting out the lower signals. So effectively, as this is a low pass filter, the lower the frequency, the more that frequency is going to come through. So if I take this down, back down to the 500 hertz, it's just, see, I'm getting pretty much all of that frequency. So let's change that out to, let's say, a higher capacitance, and I'm going to see if that increases or reduces the point at which it starts to attenuate my signal. So let's turn that channel off. Let's get me the next one, which is going to be a 220 nanofarad. 220, I don't know if you can see that on there. I can get that in shot. Yeah, I'm not sure. 220 nanofarad, that's 22.22. So let's just whip this capacitor out and put this one in. Right, so I'm going to leave it on 500 hertz, and I'm just going to turn it on and see what it gives me. Well, it looks like it's already attenuating, because actually with a 220 nanofarad it starts to attenuate at about 723. So that's at 720 hertz. So I suppose thing is that 3 dB below my original. I know it looks sort of like it was when I used the 100 nanofarad. So without sitting here and doing all the dB calculations, I wouldn't really know, but I know it seems to be attenuating, and I take it that as I turn this up, it's going to seriously attenuate it even more. 1.6 is where the 100 nanofarad was supposedly starting to attenuate it, and as you can see on the scope now, it's being attenuated a lot more. There's a lot less signal coming through. That's at 2. Take it up to 3. I'll crank this all the way up to 5 kilohertz. We've got absolutely virtually no signal left coming through there. It is very, very small. So the higher the capacitance, even though I've left the resistor the same, I'm getting a lot less signal through. So let's use a smaller capacitor than the 100 nanofarad, like a 47 nanofarad. So we just wind this back down to my 500 hertz. There we go, and change this capacitor out for a 47 nanofarad. Get them out. There we go. We now have a, see if I can get this in shot. Not focusing very well at that point, is it? Lighting's not brilliant neither. 47 nanofarad. Bit fuzzy, sorry about that. Whip that one out. Getting the 47 nanofarad. So supposedly I should have a higher frequency because now I've got a lower capacitance. So still half a volt, still 500 hertz. Turn that on, and yeah, obviously we're getting pretty much most of that signal through. I've actually calculated it being 3.38 kilohertz or 3.4. So let's turn this up to, and it is attenuating it, but is that the -3 dB frequency at which we'd say that's 3 dB? So that's effectively my cut-off point where it starts to really cut off the signal. So if I turn it up a lot more, it should very quickly attenuate, which it is, it really is, shrinking that signal way past 5 kilohertz. We're now on 6. So redo this signal, sorry, wrong way, and crank this all the way up to something like 10 kilohertz. And there you go, you can see it is being quite heavily attenuated, but it's giving me more frequency much lower down before it starts to attenuate that signal or heavily attenuate it. So we come back down to the 3.4, which is about where the signal is starting to be at that -3 dB. Its supposed cut-off point, yeah, looks about the same as the other ones. Of course, the same sort of phase shift that we've got with all of them. So let's turn that back down to my 500 hertz, and choose another capacitor. This time I'm going to go even smaller to a 15 nanofarad capacitor. Get one of them out. Again, I'll show it, but I doubt it's going to focus on this. Just doesn't want to do it today. 15 nanofarad. Right, whip that one out. It's the 47 out, and we've got a 15 nanofarad in there now. So now I've got 15 nanofarad. Turn that on, and this time, because we've got an even smaller capacitor, we've got an even higher frequency at which it will start to cut off at, which I've calculated to be about 10.6 kilohertz. So at 500 hertz I'm getting everything through, the whole signal, no attenuation, it's all coming through. So if I now turn this up, I'm going to have to turn it up quite a bit and do the horizontal. There we go, and just crank this right the way up quickly up to something like 5 kilohertz. There's 5. Small attenuation, because I know it starts to attenuate before you actually reach the frequency cutoff point. And let's crank this right up then to the 10. As you see, it is attenuating as I crank this frequency up, but not by a great deal. It's only slightly attenuating that signal, and I want it up at 10.6. so 10.6, there we go. Again, have I got my -3 dB from the original signal? It looks about right, same phase shift. So if I now take it above that, this signal should be attenuated really heavily very quickly. So 11, 12, and it is, but it seems to be taking longer to attenuate that signal down to a really low level. So it seems to me that the higher the frequency that we're dealing with, the more it takes to actually decrease this signal as we turn the signal up. So that lower capacitance allows more signal through for longer, and this is all the way up at 20 kilohertz now. As you can see, it is quite a significant attenuation, but not as much as, say, like with the 220 nanofarad. That very quickly seemed to attenuate the signal once it went past its I know the cutoff frequency of which we expected it to attenuate. So from 10.6 up to, let's take up to 20.6. I don't know, it attenuated it I don't know how much. Again, I'd have to sit here and do the calculations, which I'm not interested in doing this time. I just want to see it give me that attenuation as I crank this frequency back down to my 10.6, and you can see it increasing again. There we go, 10.6. That's supposedly my cutoff point. So let's change this now, this capacitor, to something huge in relation to what I've been doing. The largest one I had was a 220 nanofarad, so I'm going to shove in a 1 microfarad capacitor. That's really going to give me a low frequency, so anything too high at all is going to get cut off. So let's just turn the signal off, whip that capacitor out, and then here, don't know if we can see it, see if I can get it in shot, that is a 1 microfarad, and in it goes. So this I've actually calculated at being 159 hertz. So let me just crank this frequency down. Oh, turn the knob the wrong way, never mind. I've now got it on 500 hertz, which is what I had it on when I started the whole thing. So turn the signal on, and supposedly we're already attenuating this, because the cutoff point on this is, let me just turn it up, at 160 hertz. So I've got 159, 160, so which is where the minus 3 dB should be about. So I'm expecting, as I turn this up beyond that frequency, I'm really going to attenuate that signal. But let me just take this down to 100 hertz, and we've already got some attenuation in there. So as I crank this up, we're now at 200 hertz, 300 hertz, 400 hertz, 500 hertz, which is my starting point with all the other capacitors. I've already got a massive loss of signal. So anything that's high frequency at all, in any way, shape or form, is actually being got rid of. So let me just keep turning this up. I want to try and see at what point that frequency almost disappears. So I'm at 1 kilohertz. Turn that. I'm at 1 kilohertz now. So I'm just going to really crank this up now. That's 2 kilohertz. 3, 4 kilohertz, and then we'll go up to 5 kilohertz. And you can see it's got to a point where some signal always seems to be getting through, and it doesn't seem to be taking it off any more than that. So that's at 10 kilohertz. Turn it the wrong way. But see, at 10 kilohertz, we've almost killed off that signal, because we're only expecting it to, the cutoff point is 159 hertz. So at 10 kilohertz, there is literally no bass frequencies left in there. There's no low frequencies at all. So yeah, that is a low pass filter. Really quite a simple little thing, and it seems to work quite well. Obviously you don't get an exact frequency, it doesn't come along and go 159 hertz. No, it doesn't do that. It doesn't just suddenly cut off. We get it starts to cut off beforehand, and then we get minus 3 dB at that point, and then it cuts off quite quickly. And the higher the frequency we're cutting off at, the longer it takes to actually reduce it down to 0, whereas the lower frequencies, if we're talking about like the 159 hertz, it much more quickly reduces that frequency once we get above that to almost nothing. So yeah, that works just fine. So there you have it. Low pass filter, very simple. A range of capacitors to see what frequency I was going to get through. I started with, well, I put these in order of capacitance. So let's start with this 1 microfarad. I didn't show them in order when I actually did it on the breadboard. I just chose one and went through, but this is the largest capacitance, 159 hertz from 1 microfarad. So that was its cut-off point, and that seemed to well, I was going to say let through a lot, but it didn't let through much. So it was very low frequencies that it was dealing with. Next one was 220 nanofarad, a big jump there, but then cut-off point 723 hertz or 720 hertz, whatever. It's about that, you know, we weren't talking exact. That was the cut-off point, so it allowed a lot more frequency to be seen at the output that wasn't allowed through the capacitance. 100 nanofarads, cut-off point was 1.59 or 1.6 kilohertz. 47 nanofarad, 3.38 kilohertz. And then 15 nanofarads, 10.6 kilohertz. And also with that one, as you increased that frequency, it didn't attenuate it in the same way that the 1 microfarad. With the 1 microfarad, it very quickly attenuated that signal down to virtually nothing very quickly, whereas with the 15 nanofarad there was still quite a lot of frequency coming through to the output, even when I turned it up to like 20 kilohertz. So it wasn't attenuating it quite as quickly. There is an equation supposedly to work with defining how quickly it's going to attenuate after the cut-off point, but that's not what I was looking for. What I was looking for was changing the capacitance changes the frequencies that I see at the output, and that's quite basically it. That's what I've got, and it seems to me that the higher the capacitance at this point, the more it sends frequencies down to ground. So if I put in something like, let's say, a 10 microfarad capacitor, I'd see almost no frequency out here on this low pass filter, because it'd only be passing out the very lowest of frequencies, whereas obviously with a 15 nanofarad, very small capacitance, it was only allowing the really high frequencies to be passed to ground. So I was seeing a lot more at the output. So I suppose it all comes down to what do I want to see at the output, depending upon what the cut-off point is. So I mean, 100 nanofarad, that seemed quite good. If I was looking at low frequencies below, say, like 5 kilohertz, well, below 2 kilohertz really, I'd want to see them. I could use 100 nanofarad. That would sort of give me the sort of output. I know it can be refined a lot more and made a bit more specific about what you want, but that seemed to work. That seemed to demonstrate the principle that the larger the capacitance, the more the frequency is sent to ground. The lower the capacitance, the more you see that frequency at the output. And you see everything that's below that. Low pass filter. RC, passive low pass filter. Very simple, quite easy. Only requires 2 components. I'm sure I'm going to try and employ that in some circuit somewhere, because it is basic filtering and I will need it in audio circuits. So I'll have to have a go at that later on, once I've had a look at some other filters as well, which I need to do now, because obviously there are other filters to look at besides just the low pass filter. So onwards with filtering, I suppose. If you didn't like this video, you know what to do. But if you did, give me a thumbs up, subscribe, and all comments are welcome. See you next time.